Okay, so the first thing that we need to cover in C3 is actually our states of matter. So you need to know that there is 3 states of matter: solid, liquid, gas. In a solid, the particles are arranged in regular repeating patterns, and so all the particles are touching and they can vibrate. In a liquid, remember that the particles are still touching, but we've got bigger gaps between them and they are not uniform in their pattern. In a gas, there are large gaps between the particles because they're flying around at high speeds in random directions. So we've got lots of gaps between those particles. Then we move on to the idea that to compress something, you'd need spaces between the particles, and that's why we can compress a gas. Okay, so the next mini topic here is ionic bonding, okay? Ions are stable, so they will always have a full outer shell. And ionic bonding is how we get to that full outer shell. So the first thing that we look at is sodium chloride, the formation of sodium chloride, and we can picture that as a dot and cross diagram. Essentially, we know that sodium is in group 1, chlorine is in group 7. That means that sodium has 1 electron in its outer shell, chlorine has 7. So that 1 electron in the outer shell of sodium is lost to the chlorine atom, so that chlorine atom gains 1 electron. That means that the chlorine has a full outer shell, and so does the sodium now that 1 electron has gone, and that forms 2 different ions. We've lost that electron, that means we have more protons than electrons, so a sodium positive ion, so Na+, and then that chlorine has gained 1 electron, so we get a Cl- ion, and that is essentially ionic bonding with dot and cross diagrams. But there are a few other diagrams that we need to be aware of. So sometimes dot and cross diagrams only depict the outer shell, like this, and sometimes it will just be written as the ion form with big brackets around, so Na in brackets and then the positive charge. And remember that just 1 sodium atom is bonding to that 1 chlorine atom, so we're just forming NaCl. Okay, there's no little 2s or anything in that, or little 3s. There's no numbers, just NaCl. So ionic compounds are formed when metals react with non-metals. That's a key fact, particularly for 1 markers. Basically, the metal atom really wants to lose the electrons from its outer shell so it can gain a full outer shell, and the non-metal really wants to gain electrons to make a full outer shell, and that would leave them both with full outer shells, which is the ideal because that means they're stable. Ions are held together by very strong attractive forces between oppositely charged ions. That means that ionic compounds are very, very strong and therefore have high melting points, melting and boiling points. For example, sodium chloride will not melt easily. And it's really important that we recognise that this electrostatic force of attraction acts in all directions, and that therefore means that all ionic compounds form giant lattices. Metals always form positive ions and non-metals always form negative ions. Please learn that, it makes your life so much easier. The next topic is how to make a formula. If we have magnesium 2+ ion and we have an oxygen 2- ion, we've got 2+ and 2-. That means those charges can cancel each other out. They're balanced essentially, and that means that we're just going to need 1 of each ion, so we're going to write MgO. That would be our formula for magnesium oxide. However, if lithium wants to bond with oxygen has it forms a 2- ion, and lithium, because it's in group 1, forms an Li+ ion. Now we've got 1+, but we've got 2-, so we're going to need another lithium+. That means that we are going to bond with 1 O2- ion, 2 Li+ ions, so we're going to write Li2O. There are 5 compound formulas that you need to know off by heart because you will not be able to come up with this in the exam. First one is sulfate, that is SO4 2-. Next one is nitrate, that's NO3-. Carbonate, CO3 2-. Hydroxide, OH-, and ammonium, NH4+. On to properties of giant ionic structures. Giant ionic structures conduct electricity in their molten and aqueous states. This is because in a solid structure, the ions cannot move and therefore they cannot carry charge. Giant ionic structures have very high melting and boiling points, and this is because they have very strong electrostatic forces of attraction that need to be overcome so that structure can change state. So in an ionic solid, ions are in fixed position in a giant lattice. They can vibrate, but they cannot move around, and this will not conduct electricity. Ionic molten compounds, so when we heat up something, so if we heat up a bit of lithium, the high temperature here provides enough energy to overcome the many strong attractive forces between the ions. That means that the ions are free to move and carry charge throughout the structure. That does conduct electricity. Ionic compounds in solution, when we mix ionic compounds with water to separate out those molecules. Now, these water molecules separate the ions from the lattice. That means that the ions are free to move around within the solution, therefore carry charge throughout the structure, and therefore an ionic compound in solution does conduct electricity. In ionic giant lattices, oppositely charged ions are attracted to each other. Opposites attract, sames repel. This attraction forms a strong ionic bond. The charge on an ion acts in all directions, and the ions arrange themselves into a lattice structure involving huge numbers of ions, which is why we call them giant structures, and they are visible to the naked eye. However, there is another type of bonding. This is covalent bonding. We are now going to compare ionic compounds with covalent compounds. So, ionic bonding is between a metal and a non-metal, whereas covalent bonding is between two non-metals. In ionic bonding, electrons are donated or received. That means they form ions. In covalent bonding, electrons are shared, so no ions are formed. In ionic bonding, we can conduct electricity in molten and aqueous states. All or most covalent compounds cannot conduct electricity even in solution. Ionic compounds have strong ionic bonds. In covalent compounds, we have strong covalent bonds. In ionic compounds, we have very strong forces of attraction between molecules. In covalent compounds, we have very weak intermolecular forces. And ionic compounds actually dissolve in water. There are three ways that we can portray covalent bonding. The first one is an energy level diagram. Here we can see H2O, two hydrogens bonding to an oxygen. Each hydrogen is sharing its outer shell electron, and the oxygen atom is sharing one electron for each of the hydrogens. That means that we have 2 electrons in the outer shell of the hydrogen, so they are full, and we've got 8 in the outer shell of that oxygen, so that is full, so we've got stable. That means that it's correctly covalently bonded, and you might need to, it's very, very likely that you'll have to complete an energy level diagram for covalent bonding in your exam, so this is really important to learn. Then we have dot and cross diagrams, which only depict the outer shell of each the oxygen and the hydrogen, however without the shell itself, just their electrons. And then we have a stick diagram, which shows a line for bonding, essentially for a pair of shared electrons. So we'd write H2O as H, line O, line H. If we have 2 lines, like this one here, that shows that that oxygen is sharing more than one. So if it's got 2 lines, it's sharing 2 electrons with a carbon. And I'm just going to pop in here the idea that as we heat compounds, particles within them will vibrate, and if they vibrate with enough energy, electrostatic forces between them will break and the solid will melt. However, there are limitations with the diagrams that we've just been using. Number one is they depict electrons as solid spheres, which they just aren't, and they don't show forces between the molecules. With covalent bonding, it's really important that we get our head around the idea of simple molecules. Simple molecules all have low melting and boiling points. They are mostly gases and liquids, and this is because although the covalent bonds between them are very strong, that means that atoms are held together very tightly, the individual molecules are separate from each other. There is a force of attraction between these individual molecules. These are called intermolecular forces, but these are very weak, and only a small amount of energy is needed to overcome these. Simple molecules also do not conduct electricity. They have no overall charge. They are neutral and therefore cannot carry charge. However, we also have giant covalent structures. Covalent bonding leads to the formation of substances with different types of structure. The small molecules that we've just been looking at, where a fixed number of atoms are joined together by covalent bonds, but we've also got giant covalent substances which contain many different atoms joined by covalent bonds. Properties of giant covalent structures. They have high melting and boiling points. They are solids at room temperature, and this is because they have large amounts of energy are needed to overcome their strong covalent bonds. They do not conduct electricity. Most have no charged particles that are free to move, so cannot conduct electricity. Graphite is a form of carbon, and it is an exception to this rule because graphite can conduct electricity. In giant covalent structures, atoms are joined to each other in a regular arrangement. And there is no set number of atoms joined together in this type of structure, which means that sometimes they can be really, really big. We then look at some examples of these giant covalent structures, and our first one is diamond. Diamond is naturally formed. Each carbon atom connects or bonds to another 4 carbon atoms. Really important you learn that. Every carbon atom shares each of its valence, so outer shell, electrons, and each carbon atom forms a covalent bond with other atoms. Its properties, well, diamond is very hard. It has a rigid, uniform 3D structure. It has high melting and boiling points. It's insoluble in water, which means it doesn't dissolve in water, and it does not conduct electricity because it has no free electrons. All of the electrons in each carbon atom are being bonded together. There's no free electrons to carry charge throughout the structure. Therefore, diamond does not conduct electricity. We then have silicon dioxide or silica, and this is the main compound found in sand. It is an example of a substance with a giant covalent structure, and atoms are joined together in a regular arrangement. There is no set number for the amount of atoms joined together. However, each silicon is bonded to 4 oxygen atoms, and each oxygen is bonded to 2 silicon atoms. It has a very high melting and boiling point. It cannot conduct electricity, and it can be used to make glass. And then we have graphite. Each carbon connects to 3 other carbon atoms. Each carbon atom shares 3 out of its 4 outer shell electrons. This means that 1 electron from each carbon atom is delocalized and free to move between the sheets. This forms lattices or sheets of carbon atoms, and the atoms within the lattice are held by covalent bonds. However, the lattices themselves are held by weak intermolecular forces. And then there's graphene, which is just 1 layer of graphite. That means it's 1 atom thick, it's very strong, completely flexible, and very conductive, with sellotape being used to discover and obtain graphene itself. Graphene is transparent, incredibly light, and hard. Graphene could be used in aerospace, paints, electronics. Other uses include making batteries 1,000 times smaller, forming and making unbreakable phones, and aiding the filtration of water. And then we have fullerenes, which are essentially hollow cages of all shapes and sizes. The first had 60 carbons arranged in hexagons. Now, fullerenes have a very high tensile strength, and that leads to the development of reinforced composite materials like tennis rackets. Composite materials are just 2 or more materials with different properties. Fullerenes also have a very high electrical and thermal conductivity, and this is because their bonding is like that of graphite. There are delocalized electrons that can carry charge and heat throughout the structure. Their uses include drug delivery to the body. They can target specific cancers, lubricants just like graphite, and catalysts, and this is because they have a very large surface area to volume ratio. Properties of graphite: it's brittle, soft and slippery. It has a high melting and boiling point. It's insoluble in water, and it conducts electricity, as its free delocalized electrons can move between the sheets and carry charge. It can be used as a lubricant because the sheets can slide over each other. And then we have polymers. Polymers do not conduct electricity. Polymers are actually made of alkenes, which we'll look at later in C9. But essentially, there is a unit that is just repeated and repeated and repeated. And we write this using this diagram here. It's really important that the lines go through the brackets, and we've got that N there. That N stands for the number of times that single unit is repeated. Polymers are essentially really long chains of compounds. And then we have metallic bonding. Metals form a giant structure, and giant structures are those that you can see, for example, diamond, copper, and sodium chloride. These tend to have high melting and boiling points. Simple structures are too small to see. We're going to look at the properties of metals first. Well, metals are strong. They are solid at room temperature, the only exception being mercury, which is a liquid at room temperature. They are shiny, they conduct heat and electricity, and they are malleable, which means they can be hammered into shape without smashing, and ductile, which means they can be drawn into long wires. Metals consist of positive metal ions surrounded by a sea of delocalized electrons. It's essentially the positive metal ion that bonds to a delocalized electron, forming a metallic bond. That is metallic bonding. But if we've got aluminium 3+, rows of aluminium 3+ ions with the relevant sea of delocalized electrons versus a row of sodium plus ions and its delocalized electrons, the aluminium is essentially going to be stronger. That's because there are more electrons involved, and because it's stronger, it will have a higher melting and boiling point. So essentially, outer shell electrons delocalize and are free to move. This forms the sea of electrons and leaving positive metal ions. There is attraction between the negative electrons and the positive ions, and this holds the metals together like a glue. The metal ions are held tightly in neat rows that can slide over each other. Metallic bonds are strong and a lot of energy is needed to break them. Thus, most metals are solid at room temperature. This is because there are strong electrostatic forces of attraction that hold the positive ions closely with the negative electrons. Metals conduct heat. The ions are so close together that they are able to pass heat on to the next ion by vibrating, and they conduct electricity because the sea of delocalized electrons can carry charge throughout the giant lattice structure. They are ductile and malleable. All ions in a metal are the same size, so they can slide over each other very easily to change shape. And this leads us onto metal alloys. An alloy is a mixture of two elements, one of which is a metal. Alloys are essentially improved metals. For example, steel is made of iron and carbon. Steel is stronger than iron and it doesn't rust. So in a pure metal, all atoms are the same size and the same shape. This means that the layers can slide easily, which is why metals are malleable. Alloys, however, contain atoms of different sizes. This distorts the layers, making it harder for the layers to slide, and this makes alloys stronger than pure metals because those layers can't slide over each other anymore. And then there's just a note that intermolecular forces increase with increasing size of molecules. Therefore, polymers have high melting and boiling point. The limitations of the models. Most of the models that we use are 2D, which of course is incorrect. Also, our 3D models portray the atom at incorrect angles. Dot and cross diagrams depict electrons as either crosses or dots, but in reality all electrons are identical and are constantly moving. For giant structures, we cannot reflect how many are bonded, and bonds actually vibrate, bend and twist. They are not rigid or solid.